As we already explained before, the estimate that we find is just a single number that we found by chance in our sample. If we would take another sample, we would find another value for our estimate. So there is a level of uncertainty in the estimate, and we also have to report this uncertainty. How is it best to report uncertainty? We could give the estimate and a standard error. But then again, just these two numbers are very difficult to interpret and do not give any intuitive idea about a value for a population parameter. Therefore, it would be better to report the estimate and an interval around that estimate that maps the uncertainty. So instead of giving only one estimate for, in our case, mu, the population mean, we will give an interval of estimates that contains mu with 95% probability. So we will give a range of plausible values in such a way that if we have this range, then in 95% of the cases, so in 95% of the studies that we execute, the true value of mu will lie inside this interval. Suppose for now that we exactly know the population variance sigma squared. Later on, we will relax these conditions. The interval that contains plausible values for a population parameter is called the confidence interval. Please follow the link on the bottom of the slide and take a look at the video clip. We know that either exactly or approximatively, the sample mean follows a normal distribution. A normal distribution with a mean mu and a standard error of sigma divided by the square root of n, or a variance of sigma squared over n. We also saw that the reference interval for x bar, the 95% reference interval, would then be mu plus or minus 1.96 times the standard error. So the mean, the population mean plus or minus the quantile for a 95% interval times the standard error sigma over the square root of n. However, we don't want an interval for x bar, we want an interval that contains mu with 95% probability. So we have to rewrite this interval in such a way that we find an interval for mu. This can be done very easily by following simple calculation rules. If you look at the interval, you have an x bar in the center and mu on the outside. So you want to have mu in the middle, thus you will subtract mu from all the terms. After you subtracted mu, you have x minus mu in the center. You want to transform this to mu, so you multiply by minus 1, and then you have mu minus x bar, so you add x bar to every term. And so you find an interval around mu, which corresponds to x bar plus or minus 1.96 times the standard error sigma over square root of n. And for this interval, we know that the probability is equal to 95% because we started from a 95% reference interval. So the probability that my true population mean lies in this interval is 95%, and this interval we call the 95% confidence interval for mu. However, in practice, this interval can hardly ever be used. Why? Because we don't know sigma. We have assumed that we know sigma, but in reality, sigma is most often unknown and we have to estimate it. So we estimate it by the sample standard deviation S, but by using an estimate instead of an exact value, we introduce more uncertainty within this interval. So the interval that you see, x bar plus or minus 1.96 s over square root of n, will be too narrow. Too narrow because s is only an estimation of the true value, and so it introduces more uncertainty, and so your interval has to be wider to still be certain to contain 95% of all the plausible values. So we need to widen the interval. We widen the interval by changing the quantile that we use. So instead of using the 97.5 percentile from a standard normal distribution, we will use the 97.5 percentile from a student t distribution. A student t distribution with n-1 degrees of freedom. On the plot, you see in black a standard normal distribution, and in color you see different t distributions, so student t distributions for different degrees of freedom. The red one has 1 degree of freedom, the blue has 5 degrees of freedom, and the green one has 30 degrees of freedom. What do you see on this plot? you see that the shape of a t-distribution is very similar to the shape of a normal distribution. Furthermore, you also see that with an increase in the degrees of freedom, you get a better and a better approximation of the normal distribution. So actually, the normal distribution would be a t-distribution with an infinite number of degrees of freedom. From the plot, you also see that the center of the distribution is 0, the same as the standard normal distribution, and you see that for a t-distribution, the tails are heavier than the tails of a standard normal distribution. If you then change the normal distribution by a t-distribution, your 95% confidence interval for the population mean becomes x bar, the sample mean, plus or minus the quantile of a t-distribution, times the sample standard deviation over the square root of n. And this interval contains, with 95% probability, the true population mean mu. The percentiles from a t-distribution can be found either in the tables, which you can find in the appendix of the course, or you obtain them from the software. From the definition of the confidence interval, you see that the uncertainty decreases, so the interval becomes smaller if we have more measurements, so if n increases, because then we divide by a larger number. And also there is less uncertainty if there is less variation on the data, so if the data are more homogeneous, because in that case S will be smaller, and so also then your interval is less wide. Now, what is the interpretation of such a confidence interval? It does not mean that you have 95% probability that mu lies in the interval that you found. Why not? Because the interval that you found is a fixed interval. This means that mu is either in this interval or not, but there is no probability. It is a deterministic interval because once you take measurements, you obtain values for the interval, so the begin and the end point of the interval, and then mu lies either inside the interval or outside the interval, but there is no probability associated with this. What it does mean is that in 95% of all the cases, this interval that you calculate will contain the true value of the population parameter mu. So if you repeat your study 100 times, then on average, in 95% of the calculated confidence intervals, the true value of mu will be contained. This is because your variation is in the sample. So if you draw a different sample, you get different observations, and with different observations you get different values for x bar and s. And thus the confidence interval will also change with the sample. So there is variation in the confidence intervals, but the formula that we use guarantees us that in 95% of all the cases, the interval that we calculate will contain the true value of mu, so the true population parameter. So if we have 100 samples and we get 100 confidence intervals, then on average 95%, so 95 of those confidence intervals contain the true value of mu. What will then be the 95% confidence interval for the mean sulfate concentration? We know that the mean sulfate concentration from the sample was 61.92 micromolars per liter, and we calculated the standard error before as 0.85. To calculate the confidence interval, we also will need the percentile. So the percentile that we are using will be the percentile of a t-distribution, because we estimated the standard error, and a t-distribution with 37 degrees of freedom, because we had 38 observations. To determine the quantile, we take a look at the table for the t-distribution. The layout of this table is a little different from the layout of the table of a standard normal distribution. What is given here are the quantiles themselves. So what you have to do to find the quantiles is look in the column, in the first column, for the degrees of freedom that you are using, and in the top row you will look at the percentile that you need. In our case, we need the 0.975 percentile because we want to have a 95% confidence interval. So this is an interval that contains 95% of the data in the center, 2.5% on the left and 2.5% on the right. So we have to look at the 97.5 percentile. This is in the fifth column. For the degrees of freedom, we would need to use n equal to 37. However, the table does not have a value for n37. It has values for n equal to 30 or n equal to 40. So which one to take in that case? When you look at the confidence interval, you see that the boundaries are determined by the quantile, the 97.5% quantile, for a t-distribution with 37 degrees of freedom. When you look in the table, you see that the t-value for 30 degrees of freedom is 2.042 and the value for 40 degrees of freedom is 2.021. You know that 37 degrees of freedom will lie in between 30 and 40 degrees of freedom, and so the exact quantile that you would need to use lies between those two values. Then which of those values will we have to use? Just reason about it. If you have your confidence interval, you know that this confidence interval contains, in 95% of the cases, the true population mean mu. This confidence interval is determined by the quantile of your t37 distribution. If we plug in the value for t40, we make the interval smaller, because the value of t37 is larger than the value of t40, so the confidence interval becomes smaller. And in this case, there will no longer be 95% probability associated with the interval. Because you make it smaller, you also reduce the probability. So what you have to do is you take the first value in the table, which is larger, or in this case corresponds to a lower degree of freedom than the one that we would have to use. In this case, we use a value which is larger than the value that we needed, and so the interval is wider. The interval is wider, meaning that it will contain a little more than 95%, but at least it will also contain 95%. If we take a smaller value, it will not contain 95%, so we always go for the first value, which is larger than the value which is not in the table. And thus, in this case, the value that we will be using is 2.042. And then the confidence interval becomes the mean, the sample mean, 61.92, plus or minus this quantile, 2.042, times my standard error of 0.85. On the other hand, we could also determine the quantile using exact values through the computer. So in your computer program, in our case in R, you will be able to find the quantile. And then if you look at the quantile, the 97.5 percentile of a t37 distribution, you find a quantile of 2.03. This value lies indeed between 2.042 and 2.021. And so the exact 95% confidence interval for the mean sulfate concentration is 61.92 plus or minus 2.03 times 0.85, or an interval that goes from 60.19 micromolars per liter to 63.65 micromolars per liter. If you then compare it with the 95% reference interval, so recall the reference interval was mu plus or minus the quantile times the standard deviation, you had that it was a reference interval from 51 to 72, and so the reference interval is wider than the confidence interval. And this is true in general. Usually the reference interval is wider, is broader than the confidence interval, because the reference interval uses the standard deviation and the confidence interval uses the standard error. If we then want to calculate a 99% confidence interval for the mean sulfate concentration, the only thing that we have to change is the quantile, the percentile that we want to use. So instead of using a 97.5 percentile, we will now be using a 99.5 percentile. We have an interval of 99%, so it means that 1% is outside of the interval, which means that it's 0.5% is on the left outside and 0.5% is on the right outside. To find the exact value, you can use the following code in R. So you type Qt for the Q for quantile T for T distribution. So Qt gives you a quantile of a T distribution. Then you type the quantile that you want, so 0.995, followed by the degrees of freedom, in our case 37. The answer that you get will be 2.715. And the 99% confidence interval runs from 59.61 up to 64.23 micromolars per liter. On this slide, we visualize the interpretation of the confidence interval. As we said before, a confidence interval, a 95% confidence interval, means that if I would take 100 samples, then on average, 95 of the samples give me a confidence interval that contains the true value of mu. So what we did in this case is we took a distribution, a standard normal distribution. We set alpha equal to 5%, so 1 minus alpha is 95%, so we are looking for a 95% confidence interval. And then we took a sample of 30 observations, and with that sample we calculated a confidence interval. So we have our first sample with a first confidence interval, which is the first line that you see. We then repeat this procedure 100 times, so we took 100 samples and we obtained 100 confidence intervals, which are drawn in the plot. The true value of the population mean is 0, so a vertical line is drawn over 0. And we can then compare each of the confidence intervals with this line. Does the confidence interval contain 0, yes or no? If it contains 0, then the confidence interval is drawn in blue. If it does not contain 0, it is in red. For our particular case, 7 of the calculated confidence intervals do not contain 0. However, this is not in contradiction with what we said about confidence intervals. A confidence interval will contain, on average, 95 out of 100 times the true population mean. But we also know there is variation in our samples, and so it will not always be exactly 95 out of 100. In our case, we have 93 out of 100. If we took 100 different samples, it might happen that it's 97 or 99. So on average, if we would take an infinite number of samples, then 95% of the confidence intervals will contain the true value. But here there is always some variation. So here we see that 93% of the calculated confidence intervals do contain the value, 7% does not contain the value 0, but that is logical, it is due to random variation in the data. Similar to what we said before, this also holds if you look at studies. So if instead of different samples, we take different studies on the same effect, and we calculate in this case a 99% confidence interval, then theoretically the confidence interval will contain, in 99% of the cases, the true population mean. To conclude, drawing conclusions based on one single estimate can be very misleading, and so it should be avoided. In statistical analysis, it is therefore the good practice to report confidence intervals. They should systematically be reported. Unfortunately, in practice this is not yet the case. Although more and more papers will cite or will give you confidence intervals, some still stick to a standard deviation with a mean. Confidence intervals are a good compromise. They are sufficiently narrow to be informative, so to give you a good idea about the true value, but they are hardly ever very misleading, so they will never be very wrong. And we can conclude that the parameter that we are interested in is lying inside of the confidence interval in 95% of the cases, so the statement that we say is correct with 95% probability. So statistics, it's important to know that statistics is never about absolute conclusions. There is always a probability associated with a certain conclusion.